In this video, we're going to close out our ANOVA lecture by discussing the randomized block design. So in a randomized block design, it's important to realize this is a design. We will do an analysis of variance to analyze the design. In fact, we're going to be doing a factorial ANOVA without an interaction to analyze the design. And why I say that is because some students think when we do randomized complete block design or randomized block design that it is its own analysis, and we kind of do write out the equation slightly differently. But we write out the terms in the equation differently, but ultimately the process that's running is the exact same process. That is the R code that you type in is literally the same R code. You don't change anything for block design. So what does change? If we're doing the same analysis, what does change? And what changes is the design. Randomized block is a design. It's not a different analysis. So blocks, as a rule, are limits on randomization. So one way that I like to talk about this is, let's say we're analyzing a laser cutter that is going to create some really cool images. Let's say I'm like making little prints for a necklace, and I have these big bars of metal, and I'm cutting out these slices, and then I'm doing something with a laser to cut a cool design in them that I'm eventually going to send to my client. So that's what's going on. So I've got a few different lasers here. Maybe I'll try to draw my laser. Pew, pew, pew. Those are my lasers. Okay. And they make pew pew sounds, I guess. So on the lasers, I'm trying to figure out which of these are these lasers working relatively the same. So I'm looking at the number of errors that they cause. And I'm cutting off slices of metal from these different bars. The problem is let's say I can only get 1, 2, 3, 4 slices of metal per bar, but I want to look at more than just 4 replications within each laser. Well, that means I have to use a second bar of metal and then run that through. The trick is that for every slice, that's what I'm actually analyzing, did it work or not? For every slice, I can't randomly assign the slice to the bar of metal. The bar just comes from this slice of metal. There's nothing I can really do about it. It just comes from the slice of metal. And remember, with our randomized design, with our the design we were doing earlier, I should be able to randomly assign it to the treatment. So in a factorial ANOVA, I've got to randomly assign every experimental unit. That is, every block of metal has to be randomly assigned to my laser, and in this particular case, it should be able to be randomly assigned to the bar of metal. But while I can randomly assign the block to the laser, I can't randomly assign the block to the bar of metal. So in this particular case, I'm limited in my randomization. A randomized block design is a design with 2 factors, bars of metal and lasers, where I can randomize in one of them, but I am limited in my randomization on the other. In this particular case, I'm limited in that I can't randomly assign the bar of metal, or the block of metal, to a particular bar. It just came from whichever bar it came from. And in this particular case, where I can do the randomization, that's going to be called my factor. And where I can't do the randomization, where I'm limited, that's going to be called my block. Now, what's really important here is that in this analysis and in this design, I do not analyze, or excuse me, I do not, well, yeah, I include the blocks in the analysis, but I don't test them. I can run a test on them, but that test is not going to be meaningful statistically. What I'm testing is the laser, and I'm just accounting for the fact that I have different blocks of metal that I have running through this experiment. So that's really important to realize, is that in the randomized block design, I don't typically analyze the block. I analyze the factor, and I just control for the block. I take into account the variation, the fact that each of these little pieces of metal came from a different ingot of metal. But I'm not actually analyzed, because I don't really care that the ingots differ or not. That's not something I'm interested in. I'm interested in the lasers. the lasers working. I just want to account for the fact that these little pieces of metal are coming from these different ingots. So again, randomized block design is a design. It's analyzed with a factorial ANOVA without an interaction effect, where I've got two factors in this particular example. So when I have a factorial ANOVA, it's going to look just like our old factorial ANOVA did. I've got the treatment, I've got the blocking factor, and I've got the error, and you'll note that I don't have an interaction effect. In this particular case, I'm going to keep the k minus 1 for my treatment, and then I'm going to use b for block to be b minus 1 is the degrees of freedom for the blocks. So b total blocks in our previous example, that'd be 3, and k total treatments in our previous example, that would also be 3. Now the error term gets the k minus 1 times b minus 1 interaction. So the error term tends to get the degrees of freedom that was formerly going to the interaction. You'll note that in this design we tend to assume no replications. Sometimes that happens, sometimes that doesn't. It really depends on how many pieces we can get out of our block. So in our previous example, we could have replications depending on how many chunks could be pulled out of our block. But if I could only pull, let's say, 3 slices of metal out of any given ingot, then I'd stick those under the 3 lasers, and then I wouldn't have any replications for the next ingot. I'd just have 3 slices of metal under the 3 different lasers, and then I'd have to cut another ingot to be able to run another set. So in this particular case, we've got our calculations are all the same as they normally were. Sums of squares over the degrees of freedom gives me the mean squares, and then the F is the mean squares treatment of the mean squares error. Again, you'll notice I'm not testing block. Block is not something that can be tested with this design. What I'm testing is treatment. All right, so looking at this example, we've got different blends of gasoline, and we're trying to figure out the miles per gallon ratings of these different blends of gasoline. Now, as a gas manufacturer, I only care about the gasoline, but I do know that people have different automobiles. So what I want to do is I'm going to get 5 cars, and I'm going to stick the gas in each one of these cars and drive it around and see how many miles per gallon I get. And then I'm going to do that for blend X, blend Y, and blend Z. So the same car is going to be used for all 3, and that way I'm going to be able to see how many miles per gallon I get for all 3. And I don't have money to go out and buy a whole bunch of different automobiles, so automobile is going to be kind of like my ingot of metal, in which case I'm going to use it for all of one run and all the factors, but then I can't, then it's all used up. So I'm going to use my automobile, try it all out with blend X, blend Y, and blend Z. Could we do replication here? Absolutely. Yeah, we could take an automobile and then retry it with all the 3 blends, and that would be a replication. That would be a little bit different than the study design that we're talking about here, where we're assuming no replication, but it could be really interesting to study and see and get more data if we wanted to with our 5 different cars. In any case, without replication, I do want to take into account that my 5 different cars may have different miles per gallon associated with the car, not necessarily with the blend of gas. So it's really important that I account for the fact that if I've got a small sedan versus a big truck, there's going to be a lot of variability in the miles per gallon, but that variability isn't error. That variability is due to a known factor. So if I don't account for the block, all of that movement gets added to error. But by accounting for this automobiles factor, I get to, instead of having all that variability go to error, have all that variability go to the automobile or to the block in the model. And then my error is that much smaller. Looking at these, I can see the mean gas mileage for each of the blocks, and then I have the mean gas mileage for each of the gas types. And then I just run the equation that I previously had for my factorial ANOVA, but now I don't have to worry about that nasty interaction factor. So I can just calculate sum of squares treatment, sum of squares for the block, and then sum of squares for the error, which you'll see is the sum of squares total minus the sum of squares from treatment minus the sum of squares from the block. And then my mean squared error is just taking, so the mean square for each of these, again, just taking the sums of squares divided by the degrees of freedom. So once I have all these, again, you'll note that for my mean squares, I took, I have 2.6 for my mean squares treatment, 12.8 for the mean squares block, and 0.68 for the mean squares error. So what would have happened if I did not have this blocking factor is all of this, actually all the sums of squares for the block would have gone down into the error. That would have made this error term massive. So when I did 2.6 divided by that error term, that would have been a very, very small number. But now, because I factored out all of that variability, the variability due to CAR, I factored that out in my model. Now I know that my error is much, much smaller. And when I take the ratio, the division between my mean squares treatment and my mean squares error, this number is much larger relatively. Now in this particular case, the value is still 0.07, so it's still greater than 0.05 of the cutoff. But actually, if I'm interpreting this, if I only had 5 cars total, I would definitely report this as a promising feature, that there is some promise that one of these is better than another to my employer if I were doing such a small experiment. In this particular case, though, the textbook definition is this is greater than 0.05, so we fail to reject the null hypothesis. That would be our textbook conclusion from this particular case. And we'd say there isn't enough evidence to determine that there's a statistically significant difference between the miles per gallon for the different gasoline preparations after accounting for the different types of vehicles we used in the experiment. And that's the cool conclusion with this, is we can make these conclusions and say things like there is a difference after, or there isn't a difference after accounting for the type of vehicle we used in the experiment, which is a pretty strong statement. Again, if I were actually reporting on this, because that p-value is so close to the cutoff, I would tell my client that. I'd say, the p is really close to a cutoff. That 0.05 is not some magical, mystical standard spoken by God on Mount Sinai or anything like that. That is just a number that we kind of use as a rule of thumb. So 0.07 is close enough to that rule of thumb for me to think maybe that's something that is worth checking into. Maybe we need to do more data, calculate more information. Maybe I need to do a couple of confidence intervals to figure out what a reasonable range of values for some of these pairwise differences are. And maybe it's worth pulling out a couple more automobiles, running a few more replications, and figuring out if there actually is a difference between these different gasoline types and the miles per gallon that they give to the vehicles. Of course, is there a difference or not is a less meaningful question than is that difference important enough, or is that difference large enough to be meaningful to my ultimately my client, and what they're going to care about is it meaning to the consumer? Does the consumer care about the difference in size in the miles per gallon between the different gas preparations? So that has been our very quick discussion of the randomized complete block design. Again, we use this when we have a limitation on randomization. That is, if I'm trying something out within one automobile, I can't randomly assign that trial to a different automobile. I'm kind of stuck with the automobiles. Now, I could have done 5 randomly selected a bunch of different automobiles and randomly assign them to the different groups. But again, that sounds pretty nasty. What made a lot more sense in this case, because I know that automobile varies greatly within the gas mileage, was to treat automobile as a blocking factor, use automobile for all of the different factor levels of the factor I was interested in, and then run that experiment. All right, this ends our chapter on ANOVA. In the next video, we'll be discussing how do we do this in R.